So here you've got a hydrophobic coin. Placing water on the coin, you have surface tension causing the round shape of the bubble on top of the coin. Add a surfactant that disrupts surface tension, again because it's amphipathic, has a polar end and a nonpolar end, and there you get elimination of surface tension. Water becomes wetter. Here you've got oil on top of colored water. Again, this is just showing that polar and nonpolar chemicals do not mix. You can physically mix them, but they will eventually separate out. You can add things such as emulsifiers, which allows your fat and water and mayonnaise to mix together, but eventually, without an emulsifier, nonpolars and polars will separate out. Here you've got an apparatus with a smaller interior diameter as the tubes move to the left, and as you can see, the combination of adhesion of the water to the glass and cohesion of water to the water is greater in the tube with an internal diameter. Again, this has an effect with the xylem of plants, pulling water all the way up from the roots to the leaves of all the tallest plants. Here you've got a jelly jar with a little bit of window screen in the cap. The hole size is important, and again, this shows that surface tension does have a good bit of strength behind it. So you can fill the jelly jar up with water and obviously just pour it right out. But if you're careful and you turn it straight up and down and then release the pressure from the water by moving your hand, the surface tension of the water between the holes in that screen is holding up the water in the jar. You can tilt the jar to one side or the other and increase the weight on that particular side, and you're going to have a loss. There is a limit to the strength of surface tension. Everything has its limits, including surface tension. And again, there is still water between those little squares, just as you see in a wet screen. Here you've got pepper on water. Pepper is denser than water, but because of surface tension, small particles of pepper will appear to float on the surface of water. It's not truly floating, but it sits on the water due to surface tension, just like a water strider would sit on the water. Those of you who are not in lab, Google water strider and surface tension, and you'll understand what I mean. Here you add soap to again disrupt the surface tension of water. Being a surfactant, soap will allow nonpolar things to kind of clump up. So you see two things with the pepper. It clumps on the surface, just like soap would surround dirt particles in your washing machine. And you have pepper not just on the top, but floating, or kind of suspended throughout the liquid, as you see here. So there's pepper in the water, not just floating on top. If you notice before their soap was added, the water was clear between the bottom and the top of that bowl. Here again shows capillary action. You have a dry thread right there with no capillary action between the fibers of that yarn. But if you soak the yarn, now you've got adhesion between the water and the fibers of the yarn, and cohesion is demonstrated by pouring water down the yarn. The water that I'm pouring is cohesing to the water that is already adhesed within the fibers of the yarn. So again, capillary action is a combination of both cohesion and adhesion, something very important to understand. This next demo, I have a balloon that I have charged static electricity by rubbing on my hair, and a little bit of stream of water, and you can see that water has got a charge, because you can pull water away from, you can affect the pull of gravity on water by putting a charged balloon out there. As you can see down towards the sink, it may be a little bit difficult to see parts of it, but you can see I am pulling that stream of water away from vertical with a charged balloon. So that is showing that water is a charged molecule, hence the polarity.